Welcome. We have covered the topics like orbit, then we went to the space segment, and then we tried the budget for the link power, and then we came down to ground segment, and in between we have studied the propagation effect, and today we will start with the multiple access technique. That is, if you remember, the satellite basic advantage of the satellite system is that it gives a large coverage area, and large coverage area means many users can use the satellite, means the satellite resource. And since many users are trying to use a common resource, so multiple people are trying to access the common resource, which is power and bandwidth, of course. And since multiple people are trying to access, it is called multiple access. The other side of it is one agency or one person or one user is accessing the satellite and giving the information to many, one to many, that is broadcasting. So, think of a reverse of broadcasting. Many users are trying to access the common resource of the satellite, and then it is either communicating with a central station that we have calculated last time and showed that ground segment, if it is very small, like very small aperture terminal, if they are trying to access from the link point of view, from the power point of view, it is more comfortable that if they communicate with a large station. So, multiple access is sharing that the resource and going to a large station, and then it may come back to the small station. So, two small stations can communicate, two VSATs can communicate, but this part of the link, which is uplink from the small station to larger station, uplink from the small part of small stations to the satellite, that is earth to space link, this uplink is multiple access in this case. Okay. So, let us see. So, multiple access, we will talk about the techniques. What will be covered? We will cover major multiple access technique. There are many of them, but major of them we will try to cover, and then we will cover the issues like power, bandwidth, that is the satellite resource, and the synchronization in case of time related issues. Then what is the capacity for those couple of multiple access techniques, what we will talk about. What is the capacity of the, I can estimate the capacity with some lot of assumptions, of course, we will take, and then combination of multiple access to enhance the capacity. Generally, we will try to cover this. So, let us get into the business. The transponders provide two basic resources for the network of users, power and bandwidth. And let us assume that Pi and Bi are power and bandwidth for ith users at the transponder. Now, transponder has some power that we have converted into EIRP. If you remember, that power coming out of the power amplifier of the transponder is then put to the antenna to focus to the service area. So, antenna gain multiplied to this is EIRP. So, here we can consider EIRP also. Now, the Pi of the each user's EIRP, each user is trying to access some of the satellite power. So, ith user is Pi, he is taking out some EIRP, that is EIRP of the ith one, and if I is equal to 1 to n, sum of all of them will equal to some power, but that total power what they will take, that is total power available from the satellite, there will be some losses, and that is we are terming it as eta p, that is efficiency of that, or eta p, some losses are there. So, full capacity of the transponder power may not be able to utilize. Now, our intention will be to make this eta p as near as 1, its maximum value is 1. So, when eta p is 1, then all the powers each user is taking together will be the available power which is available from the satellite, total power available from the satellite. Same thing can be put for the bandwidth. So, each individual users Bi is the bandwidth of each individual user, that bandwidth sum of all of them should be equal to the bandwidth available from the resource, that is the transponder total bandwidth, but may not be able to fully utilize. If eta b is equal to 1, then only it is possible. So, our intention in this multiple access is to make this eta p in terms of power in case of power and eta b in terms of in case of bandwidth, we should make it as near to 1 as possible, right. Now, improving this eta p and eta b is achieved through multiple accessing, and sometimes it can be called multiplexing in some cases. So, that is the issue. I have shown in terms of power and bandwidth, it can be done in other parameters also. The transponder resources can be shared through many ways. If we share the spectrum, that is bandwidth, is called frequency division. Then if it is multiplexing, multiplexing, if it is multiple accessing, frequency division, multiple accessing. In terms of time, if the users share the resource, then it is called time division, and then multiple access or multiplexing. In terms of code, if we share, then it is called code division, multiple accessing. Is there any other possibility? Yes. In terms of coverage area, because satellite can generate some spot beams, and that's each spot beam will cover certain area. So, if it is coverage area, it is space actually. So, it is called space division, multiple accessing. In terms of polarization, if we do polarization division, there are many possibilities. So, some of them we will try to cover here. Multiple input signals can be combined in frequency, time and code and sent to the receiver. That combination is happening at the satellite, at the transponder. Each individual is giving it separately. At the transponder, the combination is happening, and then the combined thing is broadcast down to the earth, and on the earth receivers are there, and based on the type of multiple accessing, receivers will pick up their intended signal for them. Now, if it is done, this type of resource sharing is done locally, it is, I just try to give a definition. When it is done locally, it is called multiplexing. Two baseband signals are combined at one place and sent to the receiver. So, we can call it multiplexing, and when it is from geographically distributed location, it is called multiple access. One way of defining it, like frequency division multiple access. In short, we call FDMA, frequency division multiple access. Similarly, TDMA will be there. Just let us take an example of FDMA. A part of the spectrum, this x axis is a spectrum frequency, says part of the spectrum or part of the bandwidth is taken by a station A, and another part of the bandwidth is taken by station B with certain amplitude, and each individually they are uplinking. So, it is going to the satellite, and the satellite or at the transponder, since they are frequency wise, they are band wise, they are slightly separated. So, at the transponder they are upping one after another, that is in terms of frequency, x axis is frequency. So, say this is the total bandwidth available at the transponder, it is being shared by two users. So, it is frequency division multiple accessing, but from the transponder to the receiver, when it comes down, that is on the downlink, this now it is multiplexed signal is coming down. So, the receiver has to have to receive both, they have to have a wider filter, individually they have to have a individual type of filter, knowing where they have transmitted, how much bandwidth or which part of the bandwidth is taken by which station. Those are details, but this is the concept. Initially they are transmitting at different frequency. When it reaches the transponder, it is multiplexed, looks like multiplexed, it is coming down in the multiplexed form like interleaved form in case of TDMA. Key to the multiple access is to manage this interference of the signals from each other in the detection process. There could be interference, as you can see here, that if this band is overlapping over this band, that means if the filters are not proper, then there will be interference in terms of power. So, some power of A will be interfered with some power of B or the other way. So, it is that filter that determines. Similarly, at the receiver also the filter will determine. So, transmit side as well as at the receive side, that is important. The orthogonal signals can avoid the interference. Mathematically, if we put for signals x, I, t, analog signals where I is could be 1, 2, 3 are orthogonal, if they are, then orthogonality principle says that x I t multiplied by x j t and dt over integration over infinity, when they are x I and j, when they are equal, they will be k, and when they are orthogonal unequal, they will be 0, I not equal to j. Now, since it is in terms of t, we can call it time division. If it is in terms of f, x I f, x j f, then it is called frequency division. Mathematically, it can be presented that way. Now, let us get into some of the definitions or some of the terms that is used. Let us say there is a transponder, and the transponder in frequency domain is it have this much bandwidth, and one baseband signal is occupying the full transponder. So, it is a single carrier being transmitted and received at the transponder, and which will be pushed down to the downlink. And so, in one transponder there is a single carrier, it is called single carrier part transponder, right. There could be multiple carriers. So, two carriers like our earlier examples are transmitted in slightly different spectrum band, so that they do not overlap, and then it will be called multiple carrier in one transponder. So, multiple carrier part transponder. It could be a multiplexed signal in one carrier coming, and that one carrier is occupying the whole transponder. So, carrier is one, but the channels are more. So, it is multiple channel, but single carrier part transponder, of course. This is a common example of our TV signal, our the broadcast TV, what we observe through our DTH or even through our cable. In the satellite part, when most of the operators they book the full transponder. So, they pay for the full transponder, like let us say Tata Sky or Doordarshan or Z, anybody, they take the full transponder, and in one full transponder, which is 36 megahertz, they transmit multiplexed signal. So, if your antenna is pointing to that particular satellite and that particular transponder, if your receiver or set top box is receiving, he will receive so many multiplexed channels which are coming. So, that is how the broadcast presently is being done, multiple channel in a single carrier. It is possible that multiple channel in multiple carrier is also there. So, there could be two carriers, two separate operators are sharing one transponder, and each of them is transmitting multiplexed signal, could be TV or voice or sound or anything. So, in this case the transponder is carrying two carriers and both the carriers are multiplexed. So, it is multiple channel multiple carrier per transponder. There is some form of definitions. So, let us go into the first multiple access most commonly used, which is called FDMA, frequency division multiple access. Its advantages, people started with this because it is very simple to realize. You have to have some filters. So, and if the bit rate or bandwidth requirement for each of the input is same from the each station, then the same filter can be used for the same type of input bit rate. Say everybody is transmitting some 10 megahertz. So, a filter of 10 megahertz that is required everywhere, or at the transmit station, at the receive station, etc. So, there is no need of time synchronization because continuously is going. So there is no need of clock synchronization. These complications of clock synchronization we will see when you go into TDMA. So this is one of the basic advantage people say about FDMA is over TDMA is no need of clock synchronization among the input. They can transmit any time. It is ideal, obviously they can transmit any time, but ideal when it is a continuous traffic. If you do not have traffic in one of the channel, that particular part of the bandwidth is wastage. So it is ideal for known continuous traffic. If it is unknown and non-continuous traffic, it's a problem. So it's very simple when the trunk route between telephone exchanges or trunk route of ISP, they are using satellite. They have huge volume of traffic and it is continuous. So therefore it is ideal for those cases. But it has disadvantage obviously in terms of the continuity of the traffic. Another problem is the lower power to avoid intermodulation. Okay, intermodulation we will discuss in detail, but there is non-linearity in the satellite. We have talked about it. Transponders are non-linear. So in the non-linear mode of operation, if your operating point is at saturation or near saturation, it is non-linear, then there will be interference or intermodulation that will be generated, which is spurious. We will discuss that one in much detail later, but to avoid those spurious you have to go back to the linear region, which is called back off, and so back off means you will be transmitting less power. So therefore actually your EIRP will be lower than what is the capacity, that is to avoid those spurious. So it will be lower EIRP operation. Lower EIRP operation means you can understand your link equation, the G by T of the receive station has to be more. So G by T of the receive station more means diameter of that receive antenna will be more, or the temperature has to be lower. So that is that's one of the problem of FDMA operation. That is why in the trunk route it is used where larger stations are there, only few of them and larger stations, where you can increase the gain of the antenna by sizing the antenna to larger one, and temperature also can be controlled. And of course it is not suited for variable input rates, because everywhere you have put the filter at the transmit side and receive side, and if your input varies, so the filter bandwidth has to be changed, and that has to be dynamic. So it is not at all suited, otherwise it will be very complex dynamic filter has to be designed. Let us give a quick example pictorially, which is easy, you can realize that. Say let us say there are 3 stations, and 3 stations are given two frequency bands each. Station A has F1 and F2, put a center frequency, but it is a total bandwidth. Then B, F3 and F4, 2 center frequencies, and C, F5 and F6 center frequencies, and with certain bandwidth available. Here in the diagram it is shown the bandwidths are equal. That is at the transponder. So A is transmitting for B and C. At the transponder it is occupying F1 and F2 center frequency. Similarly, B is transmitting traffic for A and C. Obviously B is not transmitting for himself, it will be transmitting for others. So it is F3 and F4, and C is transmitting F5 and F6 for A and B stations. Now at the receive station A, he will look for only the received traffic. The whole thing is now multiplexed, frequency multiplexed, and coming down in the downlink, that is the transponder. After reception it is pushing down the downlink. At the downlink it will look like the way picture is shown, B, C, A, C, A, B, like that, the stations meant for which this band is going, F1, F2, F3, F4. So if when the A station is receiving, he will look for the F3 which B is transmitting, and he will look for F5 and C is transmitting. So his filters will be at F3 center frequency with bandwidth and F5 center frequency with bandwidth. He need not have all the filters, because it's whatever traffic is meant for him he will receive, whatever traffic meant for C he should not receive. So he has to have filters at these points. Similarly, B will receive F1 and meant for B is F6. So B filters will be at center frequency f1 and center frequency f6. Similarly for C, center frequency f2 and center frequency f4. So you can see that at each station it is pre-assigned filters are located, and if the traffic is known, here it is shown as equal bandwidth. If the traffic is known that A traffic from B is coming larger and A traffic from C is smaller, so accordingly the filter bandwidth can be adjusted. This is the allocation of the transponder, which is pre-assigned and known. So the receiver filters are properly designed and they are kept. But if it changes dynamically, then you can see that filter bandwidth has to change. That's the problem. So for fixed traffic, filters are with same bandwidth. For mixed traffic also can be done, different sizing of the filters with different bandwidth, but for variable traffic, filter needs tuning with when the traffic changes. That is a dynamic adjustment and makes it much complex. So I mean, it's not that it's not possible, but it's difficult and costly, so people don't use. And then the other issue is that amplifier need to operate in the linear region at the earth station and at satellite. At the earth station also there are multiple carriers are going up for different stations. Here I have shown only 3 stations, there may be more number of stations, so multiple carrier going up. So earth station HPA has to operate in the linear region, otherwise spurious will be generated. Similarly at the satellite, so earth station uplink will have lower power. So to maintain its ERP, his G antenna gain has to be increased, since satellite antenna gain is fixed. Similarly, satellite ERP will be lower because of linear operation, and the earth station receive antenna gain has to be increased, earth station antenna should be larger. So this is the other part of the problem. One is the filter problem, another is the power problem, and you have to operate in the linear region. Now let us try to see how do we do some capacity estimates, and we will have some assumptions. Of course, a lot of assumptions will come. One of them is equal size carrier in terms of power, in terms of bandwidth, both way. All carriers are having same power, all carriers are having same bandwidth. How do you do it? So first we find out the maximum ERP possible in this transponder, assuming the whole transponder is being used for easy calculation. So what is the maximum ERP or the total C by N naught, that is the link and support from the satellite, and then find the individual carrier ERP from the station which is going up, and the individual carrier ERP which is coming out from the satellite. So from the total ERP, you know, from the satellite, individual ERP carrier ERP from the satellite will come to know, because individual stations are taking smaller bandwidth, smaller power, so their ERPs are lower. So you remember the transmission equation that C by N naught is EIRP in dB, C by N naught is EIRP plus G by T minus losses minus K. EIRP will be the in this case from the satellite we take, so it is EIRP downlink and G by T of the earth station. So EIRP, just by changing the sign, EIRP of individual carrier from the satellite is C by N naught of individual carrier minus G by T of the station plus whatever losses are coming, and K is the Boltzmann constant, if you remember. Now where is that efficiency coming in? It is the losses. As I told you that there are possibilities that if the filters are not designed properly, or because of any intermodulation or interference, some of the power will come into the wanted band, and therefore it will increase the noise, and that is where the losses will increase. So our intention is to improve the efficiency, to reduce those interference losses or spurious losses which is coming in. So let us go back to the calculation of the capacity estimate. How much is the capacity is based on this expression. These two expressions are same, only the side changes are there, only the losses will determine that how much, and in this case losses are taken inside the calculation. So estimate of the estimate the number of carriers possible from the power requirement point of view. It is very simple, that the number is the dB subtraction, log of the number is the dB subtraction of the maximum ERP satellite can support and individual carrier and we have assumed that all carriers are same. So, it is just subtraction of that, or in terms of C by n, if you do C by n naught total minus C by n naught individual, and that will be the log n p. Now, this numerical value of n p you convert into numerical from the dB. It should be rounded to the next lower integer. That is important. Well, we do many of the students, they miss this point. That is, you do go on doing the calculation as per the formula or expression given to you. You get something, some decimal point, after decimal point some numbers, and you put that one. Practically, you look at as an engineer that really can you give a fraction of a number as the how many carriers can go. A part of the carrier cannot go. NP is the number of carriers that can be supported. So, if it is coming 31.56, the 0.56 carrier cannot be uplinked. Ideally, up to 0.56 carrier can go. So, you will go to the next lower integer. Do not go to the next higher integer, because up to 31.56 it can be supported. So, definitely 32 carriers it cannot support. So, it will support 31 carriers. So, therefore, the NP will be the next lower integer. That is very important, you have to remember. And bandwidth wise, that is power wise. The bandwidth wise is also easy. Find the bandwidth available for all carriers, that is total bandwidth supported by the transponder in full transponder case. Find the noise bandwidth of the individual carrier with the modulation, filter roll off, guard band, etc. And that how do you calculate? That is the bit rate by what modulation you have used. It has a spectral efficiency. So, bit rate by spectral efficiency factor of the modulation, and then whole thing is multiplied by roll off factor of the filter, 1 plus roll off factor, that much it will increase the bandwidth. And then between two carriers you put extra band of frequency, and that in terms of percentage of the total it can be called as guard band factor. So, 1 plus guard band factor, that is the individual, I can call it noise bandwidth of the total thing. So, since time is almost up, so we will stop here and continue in the next period. Thank you very much.